Okay guys, we're here for the last part of the lecture, and this section we're going to focus on is transformations of cubic functions. So the question will be, maybe graph a function, and we're going to look at how you can graph that function by looking at how, or obtain the image of the function based on transformation of the original function. So since we're working with cubics, the original function is going to be x cubed. That's the basic function of a cubic. And then the next four transformations, we're going to look at four transformations. The first one will be 2f of x, or really n f of x, right? In the form nx cubed. That's just timesing the function by a number or a scalar. So you could think about it as scaling the function. The next one we'll think of is f of x minus 1. But that again could just be f of x minus n, right? And that would just be x cubed minus n, alright, which would just be x cubed minus n. And that again can just be thought of adding or subtracting a scalar to the function. So of course, if n can take all negative values or positive values, so this minus could be a minus or a plus. Depending on the value of n. Then the next thing to look at is what's known as reflection about the x-axis, and that just is multiplying the function by a negative number. So we've got negative f of x, and in this case we negative x cubed. And the last one we'll look at is reflection about the y-axis, which will just correspond to f of negative x, which in this case will be brackets negative x cubed. If you wanted to include brackets to show the difference between these two, it would be sort of an imaginary bracket around the x cubed. So it would be negative f of x, whereas this is f of negative x. Okay. We're going to do this by going through each of these cases individually, showing how you can solve it by graphically plugging in values, and then also showing a general method for how you go about it, and we're always going to compare it to the mother function or the original function. So okay guys, so we're on to scenario 1. So in black, put f of x, the original function, equals x cubed, and now we're going to look at the image. We're going to try and draw the function or the image of this new function, right, which is 2f of x, which is 2x cubed. Basically, this is a transformation of the original function f of x, and the function is multiplied by a scalar multiple. The scalar in this case is 2. So, before we start exploring what happens in the transform function, we're going to think of the critical values, if you'd like, of the original function, and we're going to use them to compare the two functions. That's how we're going to proceed from going forward. So the three sort of critical values I'd always recommend looking at when trying to find or obtain a function, look at, with cubic functions at least, or quadratic. Look at the x-intercept, y-intercept, and stationary points. So looking at this graph, you can already see that there's only one stationary point. Before, let's explore. To find the x-intercept, what do we do? Well, to find the x-intercept, we know that is when the x-intercept is when you cut the x-axis, and that's when y equals 0. We set the function equals 0. So 1, we set 0 equal to x cubed. Clearly, this is only satisfied when x equals 0. Therefore, we have x-intercept where at 0, 0. Right, because by definition, the x-intercept is when y is 0, and we found one at 0, so it's on the origin. That's where the x-intercept is. But now, when we think of the y-intercept, we know that the y-intercept happens when we set x to 0. Or we've seen that when we set x to 0, right, we come out with y equal to 0. So the x-intercept is the y-intercept, which is the origin. A little tip, whenever you have a function with an x-intercept or an y-intercept at the origin, that will also be the other intercept. So if you're looking for the x-intercept and you find it on the origin, then you know that that is also the y-intercept. So what we can conclude for 1 and 2, right, is we've got an x and a y end at the origin. So here, Sorry guys, it's a bit messy, but we label the point 0, 0, and that's the x and y intercept. Then we can look for a stationary point. And stationary point, like we've already found, is when you set the first derivative equal to 0, and you have a stationary point. So you know the function f of x, the first derivative of the function f dash of x. Using the power rule, we know that's 3x squared. Set 3x squared equal to 0. And what do we find when x is 0, which we also know happens when y is 0, because we've already found that. That is the stationary point. So we know we have a stationary point at the origin. Right? Now we need to classify what type of stationary point do we have. Is it a local min? Is it a local max? Is it a saddle point or point of inflection? Well, let's use the second derivative test. And we've already established the first derivative was 3x squared. So the second derivative will be 6x. Now, when we look at the stationary point, is when x is 0. So 6 of 0, or rather f double dash of 0. Assessing the second derivative at the stationary point, we get 0. And what did we say? When the second derivative is 0, that means we have a point of inflection. I'm just going to write PI, but you probably have to write that out in your exam. We've got a point of inflection, which means it's not a local min or a local max. And we can kind of see that makes sense here, because there's no minimum or maximum, even in the locality. And what we also see is the function increasing before the stationary point and increasing after. And we also see there's a slight change in concavity. If you had to carry on going, you see that this part of the function has this shape, right? So it's a concave function, whereas this part of the function has this shape. So it's a convex function, or convex area. So we see there's a change in concavity, so that makes sense for it to be a point of inflection. So now we've plotted that. So all we know is the origin. The next thing to look at is to plug in a few points. All right? Let's plug in a few points. So I'm going to suggest we plug in 4 points here. We're going to look at the points A, B, C, and D. So they're going to correspond to x1, which is going to be A. And we'll plug 1 into this function. 1 cubed just gives us 1. So you know here, we've got the point A at 1, 1. If we put negative 1 into the function, we're going to get negative 1 times negative 1 times negative 1. So we're going to get negative 1 out. So we know here, we've got the B at, sorry, let me rewrite that. Got B, oh, actually, let's put it, got B. And that's at negative 1, negative 1, negative 1. Right? And now let's look at C, which is when x is 2. When we plug 2 in, 2 cubed, we get 8. That's somewhere up here. And that is a point sort of C. And that's going to be at 2 and 8. And then we look at the point D, which is going to be when x is negative 2. And it's going to get out somewhere here. And that's going to be negative 2, negative 8. So this is just a couple of points. And of course, we have to find x intercept, y intercept, and stationary point. They all happen to be at 1 point. So I just suggested that we plug in some other points. You only really have to plug in 2 other points, one A and B, to get the shape. But we're going to plug other points so we can assess them and compare them to the transformations. But yeah, basic structure, find the x intercept, y intercept, and stationary points, your critical values. Then assess the function at 2 other points, just to see the shape of the function. In this case, I would suggest assessing it at 1 function to the right. So I would always suggest actually assessing it at 1 function to the right of the stationary point, or 1 point to the right of the stationary point, and 1 point to the left of the stationary point. You see A and B are both 1 to the right, 1 to the left, and then just for illustration's sake, I've assessed another one to the right and to the left at C and D. So we've got the general shape of the function, the original function. We've got a couple of points out. Yeah. So now let's look at the transformation. And we're going to follow the exact same method to find the transformation. So, find the transform function. First step as usual. x int, second step y int, third step stationary point. Now, to find x int, as we've already discussed, we set f of x equal to 0. So now we've got 2x cubed equal to 0. Again, we can see x is going to be equal to 0. Therefore, we've got a x int at 0, 0. So the x intercept is still at the origin. And what did I say about having an x intercept or a y intercept at the origin? Well, you know that it's also the other intercept. And you can clearly see that here because this is when y is 0 and x is 0. So we've got an x slash a y intercept at the origin. X stroke y int at 0, 0. So we know that the function is going to cross this point as well. Yeah. So, what's next? The next thing to look at is the stationary point. So again, we find the first derivative of the function. In this case, the first derivative is going to be 6x squared. Set it to 0. 0 or 6x squared only equals 0 when x equals 0. Alright? So once again, we see when x equals 0, y is 0. So once again, we find a stationary point at the origin. And we found that 6x squared was first derivative, meaning the second derivative is going to be 12x, meaning the second derivative stationary point is going to be 0. So once again, we have a point of inflection. Right? With a point of inflection at the stationary point. So we know it's going to have a similar shape. It's going to change concavity and continue increasing before and after the function. Another way you can see this is x cubed and 2x cubed are both positive definite functions. As x increases, y always increases. They increase unboundedly. If we had to now look for two other points, since we've done what we did in the first place, let's use the same points and assess them. So let's assess now. Oops. Let's make this more careful. A. Now let's do a dashed, and that'll be referring to this graph. Now, if we had to look at the function 2f of x or 2x cubed at the point 1, well, x cubed is 1 times 2, we're going to get 2. Instead of 1, we get 2. And this can be a dash, this can be 1 and 2. If we look at 2, well, 2 cubed, like we saw before, is 8. And 8 times 2 is 16, so we sum it up here way higher. So we probably don't want to put it up here, but we just note that at 2 it's somewhere up there, way past there. Alright? So now what we notice, similarly, if we look at negative 1, we'll have negative 1 cubed gives us negative 1. Times 2 gives us negative 2. So negative 1, get negative 2. It's got a point b dash here at, b dash here at negative 1, negative 2. And if we look at d dash, look at negative 2 again, it's going to be negative 16. So it's going to be somewhere down here. So we're going to have d negative 2, negative 16, d dashed, and c dash here, negative 2, negative 16. It's obviously much higher, but what we see is that we don't want to get involved up there. So if we have to join it together, it's going to look something like this. It still passes through the origin, so it needs to pass through that point, pass through this point and through the origin. Then we're going to see that little concavity change up there. Right? So again, apologies for my drawing skills, but you get the general shape. The function is going to go like that, and the same general shape, but it's kind of like squished in. Okay, if you took the original function, which you've kind of done, actually stop it. Okay guys, okay, so what we see when we connect the points, sorry for the drawing, the point goes through the point here, b dash, so we said -1, -2, which compared to -1, 2, sorry, b, -1, 1, is just, drop down. Similarly with a went through point 1, 1, now it goes to point 1, 2. Here it goes to point 2, 8, and it goes to point 2, 16, so it'll be something up here. So basically, what you've seen is the graph has sort of come in a bit. If you want it squeezed horizontally or stretched vertically, right? So for every, here, the ratio between y and x is for every one movement across in x, you get x1 cubed movement across in y. But now, for every one movement across in x, you get 2 times 1 cubed movement in y. So basically, it's just doubled or stretched out on across the y-axis, or it's just pulled vertically or squeezed horizontally. If you can see here, it's kind of squeezed in horizontally, or if you look here, it's kind of pulled out vertically. And that's what happens, and it's the exact opposite if this number was a fraction. So this is a scalar multiple that's greater than 0. If it was a scalar multiple that was less than 1, this is a scalar multiple that's greater than 1, it's not a fraction. If it was a scalar multiple that was less than 1, so if it was half, then this would be stretched horizontally or shrunk vertically. So the new function in red would come on the outside of the old function. And at the extremes here, the new function red would be above, right, the old function or the original function in black. So if it's a positive scalar multiple, so another way to think about it, if we're looking at this where it's n times f of x, when n is greater than 1, it's squeezed horizontally or pulled vertically. If n is less than 1, it's stretched horizontally or shrunk vertically. That might be a nice way of remembering it. Okay guys, as usual, the 3 steps. X end, y end, stationary point. Here we see that we're dealing with a new function, f of x minus 1, or fx minus 1, so x cubed minus 1. A lot of you can already see what's going to happen. This is just going to be the function plus or minus a scalar, or plus or minus a constant, sorry. So it would be of the form like x cubed minus k, so as a constant, or x cubed plus k as a constant. And all that is going to be a vertical shift of the graph, depending on the value of the constants here. The constant is -1, it's going to be a decrease or a downward shift of 1 of the whole graph. And if it was a constant plus, then it would be a positive shift of the value of k of the function. So let's get involved. So the x-intercept, like we said, is when we set the function to 0. So we've got x. Okay guys, like we said, to find the x-intercept, we set the function equal to 0. So we've got x cubed minus 1. The function f of x equals 0. So we've got x cubed equals 1. We just take the -1 across. And now we've got x cubed equals 1. So x equals the cubed root of 1. So obviously x is equal to 1. So one thing we notice here, we've got an x-intercept at 1 and 0. So what we notice here is that this x-intercept, unlike in previous examples, is not also a y-intercept because the x value isn't 0. So we just put that in and we've got to label it as the x-intercept. So this function goes through this point here at 1 and 0. Yeah, we can label that here at 1 and 0. The next thing we look for is a y-intercept, and the y-intercept is when x is 0. So y int in this case will be so it'll be 0 cubed minus 1, which will give us negative 1. The y-intercept in this case will be 0 minus 1. So in other words, the curve cuts the y-axis at 0, negative 1. So over here, right, will be our y-intercept. I'll just put that as y int. I'll just label it as 0 minus 1. Excuse me. Now we're going to look for our stationary point. And the stationary point again is found by us. And we find the stationary point again by setting x equal to 0 as usual. Sorry, set the first derivative equal to 0. So in this case, the first derivative is still 3x squared, because obviously the negative 1 constant fades away. Then we set this equal to 0, so f dash x equals 0. And we notice that 3x squared can only become 0 when x is equal to 0. So x equal to 0 is the stationary point, and the y coordinate of it, we just plug that into the original function, and we get 0 minus 1, and we get the y value of negative 1. So we have a stationary point at 0, negative 1. So we see that here is the new stationary point. And that makes sense because the graph's been shifted down by 1. And once again, we check to see what type of stationary point we have. Since we know the stationary point of the original function, and we know that we just a vertical shift downwards of the function, we know that the stationary point is going to be a point of inflection, but we check anyway. So 3x squared is the first derivative, being the second derivative, it's going to be 6x. Set the second derivative, we observe it or evaluate it at the stationary point. So, we evaluate the second derivative at the stationary point. The second derivative is 6x. So we evaluate the second derivative at 0, which is f double dash of 0. And what we get out is 0, so 6 times 0. And so we know immediately we have a point of inflection, which we would have already known, and we could have already told if we knew the shape of the original function, which in this case we do, since we drew it to start with. So yes, so this is going to be a point of inflection, which we can also tell because this function is always increasing. If you'd like, you can evaluate the other points. So say point A, we've already got. So point A was when x is 1, and the original function, the y value is 1, so 1, 1. Now, point A, say double dash, because it's our second transformation. We'll call this A double dash, not 1, 0, which makes sense because this one's been shifted down by 1 high value. If we look at this point, at 2, if we plug in 2 into our function, we'll get 2 cubed 8 minus 1 is 7. So we will find that the new point will be around here. It won't be our function, it will be just a lesser function. 2 and 7, which again would make sense because that's a decrease in the y value of 1. So the same x coordinate having a y value decrease of 1 from the original function, c double dash. And if we want to evaluate lastly, we can look at D, and we know the point D here was at the point -2, -8. Now the point D will be at the point -2, 7. So it'll be somewhere here. Sorry. Switch colors. It'll be here. D double dash, and that'll be -2, -7. Alright. Awesome. So what we'll find is that every point will have been brought down 1. So the graph is going to look, this is the point here, the graph's going to look like that, roughly. It's just a shift in the graph, 1 point downwards. This turned out a little bit better. My drawing skills have improved slightly. But yeah, basically we've just taken the graph and we've shifted it down by 1. Yeah. So that's the second transformation. And like I said before, when you take the original function f of x and you either add a scalar or subtract a scalar from it, all it amounts to is a vertical shift of the function in the direction depending on the sign of the constant that you're adding or subtracting. So if the constant's positive, then you're obviously adding, and so it's a positive vertical shift. If it's negative, then you're subtracting, and it's a negative vertical shift, and the length or the scale of the shift will depend on the size of the constant. So in this case, it was a negative shift because the constant had a negative sign, and it was of value 1 because the constant was 1. All right, let's move to the third. So the third transformation we're going to look at is negative f of x, which in this case would be negative x cubed. And this is what we call a reflection, right? A flexion about the x-axis. So we call a reflection about the x-axis, and we're going to plug in transformations. We'll plug in points of transformation. So we do the same thing as before. Y int, x int. Sorry, I wrote the order differently this time, but it doesn't matter. It's actually points. So before we do that, let's talk about what we mean by reflections. So when you reflect something, you put the mirror image of the function across whatever you're reflecting it across. So if you're reflecting it across the y-axis, right, if we only looked at this portion, we'd see the mirror image. If we break apart the x-axis, the mirror image would look something like this. So it just means putting the mirror image of the function across the other side. Or sorry, putting the mirror image of the original function across whatever you're reflecting it about. Now a good way to think about this is, good way to think about reflection across the y-axis would be if you had a parabola like that, right? Well then, we know parabolas have an axis of symmetry, right? And if the parabola is centered on the origin, the axis of symmetry is just the y-axis. And so the right side of the parabola is just reflected about the y-axis, or the left axis. The opposite sides of the parabola are just reflections of the other side across the y-axis. Similarly, if you had to take a parabola and flip it, right, then opposite sides, the positive and negative sides of the parabola, are simply reflections of each other across the x-axis. In which case, if the parabola was again centered on the origin, as you can put it, centered on the origin, then either side would just be reflections of each other about the x-axis, as the x-axis would just be the line of symmetry. So you can just think of it as whatever it's being reflected about is the new line of symmetry. And so what on the other side is just a symmetrical reflection of what's on the original side. Alright, so in this case we're reflecting across or about the x-axis. So whatever we see here should be here, whatever we see here should be here, roughly. So let's think of our x-intercept first. So x-intercept, we set it equal to 0, and the function equals 0. So if we set negative f of x equal to 0, we've got negative x cubed equals 0. Well, what do we find? X equals 0. Plug it back into the function, we get the y coordinate, we get negative 0, 0, which obviously makes sense. As to find the x-intercept, we've set y equals 0 anyway. So the x-intercept is 0, 0, and necessarily, since the x value is now 0, also know that that is the y-interception. So the x-intercept equals the y-intercept, which equals 0, 0, which is the origin, just as in the original function. And that makes sense because since it's on the origin, reflecting it about the x-axis makes no difference as it's centered on the origin. So we wouldn't expect that point to change. So it passes through here. Moving on, what we find is the stationary point. To find the stationary point, we do the same thing as usual. We set the first derivative of the function equal to 0. Set the first derivative of the function equal to 0. So f dash of x in this case will be negative 3x squared. Negative 3x squared equal to 0. Then x must equal 0. And we already saw from before that when x is equal to 0, y is equal to 0, and that is the origin. And so the stationary point lies on the origin. As one would expect, as this is just a reflection, the stationary point will behave the same as in the original function, but we can check that again. So if we know the first derivative, negative 3x squared, we know the second derivative is negative 6x. If we evaluate the second derivative at the stationary point, we get 0. And once again, we've got a point of inflection, which is exactly what we would have expected. So we know that at this point, the function will continue increasing, but there will be a slight change in concavity. So now, the next thing I'd recommend is, well, looking at some points. So look at the point A. Here the point A is 1, 1, but in the new function, when the value of the function, the x value is 1, so at the point where the x value is 1, the value of the function, or the y value, will be 1 cubed, which is 1 times negative 1. So the new coordinates of A, or A dash, would be 1, negative 1. So we're over here. So, and if we look on the other side, similarly at B, where the coordinates were negative 1 and the output would be negative 1 in the old function, now if we plug in negative 1 into the new function, we get negative 1 cubed, which is negative 1, times negative 1, which is positive 1. So then B dashed would be here, and you'd have negative 1 and 1. We could do the same thing for C and find that we now have find C dash is now 2 and negative 8, because 2 cubed is 2 times 2 cubed is 8 times negative 1 is negative 8. Similarly, for D, if we input negative 2, we get negative 2 cubed, which would give us, we get negative 2 cubed, which would give us negative 8 times negative 1, which would give us 8, so somewhere here. That would be D dashed, which is negative 2 and 8. So, if we had to draw it all up, I'll give it my best attempt. Please bear with me. And like that would continue further and further. But that actually wasn't too bad. What we see here is point A has been, the new point A dash is a symmetrical reflection of the original point A across the x-axis. So the distance between the 2 points is, the x-axis is now equidistant between the 2 points. That's another way of thinking about reflections or a line of symmetry, is that the distance between the line of symmetry and the 2 points is equidistant. Or the 2 points lie equidistantly from the line of symmetry. And so they become mirror images of each other about the line that they're being reflected across. And we can see the same is true for point C and point C dash, and point D and point D dash. And so we see they're just reflections of each other about the x-axis. Right. So this function is unique because when you look at the second transformation, I'm going to look at the transformation. The fourth transformation, or the last transformation we're going to look at, is f of negative x, which is equal to negative x cubed. Now, some of you might already notice that that's going to be exactly the same. So this is why this cubic that we have is x cubed cubic, which is centered at the origin and has nothing else done to it. So no scalar multiples and no scalar subtractions or additions. Well, that function is going to be equal, or the reflection of that function about the x-axis and the y-axis gives you the exact same image. Now to show that, let's look at it. What do we do? Well, we know the three tips. Find x-intercept, find y-intercept, find stationary point. Sorry. So x-intercept, y-intercept, and stationary points. Right. To find x-intercept, as usual, we set the function equal to 0. So f of negative x, or negative x cubed, has to be equal to 0. Well, that can only happen when x is 0, as you have negative 0 cubed, which equals 0. So we know that when y is 0, only occurs when x is 0. So, clearly again we see that the x-intercept is the y-intercept is the origin. So, as we'd seen before. And so we know this point passes through the origin, which we already know because we know that we have the x, or the reflection about the x-axis, which we know is also the reflection about the y-axis. But either way, we know it goes to the origin. Now we find the stationary point, and to do that we find the derivative of the function. So the derivative of the function. So here's where it gets a little bit trickier, because we're going to have to use something called the chain rule, right? Because we've got a function here, negative x, times, or raised to the power 3. So what we've got to do is we've got to get the derivative of the outer function here, right? So we don't really need to know this, but I'm just going to talk you through this. We've got the chain rule which says you get the derivative of the outer function. The outer function is negative x cubed, right? And the derivative of that will be 3 negative x squared. And you times that by the derivative of the inner function, which gives you negative 1. And so the derivative of the function will be negative 1, so negative 3 times negative x squared, which gives you negative 3x squared. So yeah, we know the first derivative is negative 3x squared. In this case, we just treated it as negative x cubed. You still get negative 3x squared. So the method we know, the power rule, would still work in this case, but strictly speaking, it would be better to think about it as a chain rule, so the derivative of outer times the derivative of inner, but in this case it would still work. So we've got the first derivative as negative 3x squared, and the second derivative now would be negative 6x. If we set the first derivative equal to 0, we know, well, negative 3x squared can only equal 0 at x equals 0. We know the y-coordinate of x equals 0 is 0. So we know, once again, there's a stationary point at origin. Once again, we know the nature of stationary point because we already know that this is just a reflection about the y-axis, so the stationary point's nature won't change. Similarly, we know what the image actually looks like because we know that in this case, the reflection about the y-axis is exactly the same as the reflection about the x-axis, and the reflection about the x-axis showed us that the stationary point remained a point of inflection, meaning that the stationary point in the reflection across the y-axis will remain a stationary point. Okay, sorry, will remain a point of inflection. So, we know the nature of this point. So now what we do is plug in the points that we used. So A, B, C, D. So, well, f of negative x, right? So, negative x cubed, well, for negative 1, we have negative 1 cubed. And so the answer will be negative 1. So, A will be, so let me make this more clear. Negative x all cubed gives us an answer. So negative of 1, so when x equals 1, we get negative 1. So the output of x equals 1 gives us 1, negative 1. So that point A dash stays the same. Similarly, if we look at the point negative 1, and we're looking at B here, the original was negative 1, negative 1. If we plug in negative 1 here, what we get is negative 1 times negative 1, which is positive 1. Positive 1 cubed is 1. And so we'll end up having, at the point negative 1, the x value of negative 1, the y value is 1, which is exactly what we saw here, at B, negative 1, 1. B will be here. And if we look at C, we'll get the exact same thing. So C is the point 2, where x value is 2, and originally we got 2 and 8 in the original function. Well, now we'll have negative 2 cubed, which will be negative 8. And so the new function will go to the point 2, negative 8, which over here, which is exactly the same as we saw in the reflection across the x-axis. And finally, if we look at the point D at negative 2, we have negative 2 times negative will just be positive 2, cubed will be 8. So at negative 2, it'll go to the point negative 2, 8, just as we saw in, can you put that here? Just as we'd seen in the reflection about the x-axis. Now, instead of looking at the x-axis as the line of symmetry, we can look at the y-axis as the line of symmetry. And you can see that A, right, is just reflected across now. The points A and B are equidistant from the y-axis. They are mirror images of each other about the y-axis. Similarly, the points D and C are equidistant from the y-axis. Well, I know in this image it doesn't quite look like it, but they are. Just poor drawing. And they are equidistant about the y-axis, and so they are mirror images of each other about the y-axis. Similarly for A and B, and C and D. And so instead of looking at it as a reflection across the x-axis, we now look at it as a reflection across the y-axis. Now so we've proved that graphically, that for a special case of x cubed as f of x, negative f of x, or the reflection across the x-axis, and f of negative x, the reflection about the y-axis, are exactly the same. They're the same image. We can also prove this algebraically as f of negative x is equal to negative x cubed, which is the same as negative 1 x all cubed, which gives us negative x cubed, right? And we know that negative f of x is equal to negative x cubed. Therefore, f of negative x is equal to negative f of x. So algebraically, we've proven that the reflection about the x-axis and the reflection about the y-axis are the same, and we've also proven it graphically. As you can see, they're the same exact image, or the same exact graph. So guys, those are the 4 key transformations you need to know And so if you remember the key tips for the transformations, the method of obtaining them is 1, find the x-intercept, 2, find the y-intercept, 3, find the stationary point, 4, find 2 points, 1 to the left and 1 to the right of the stationary point, assuming there's only one stationary point. And then the next thing I'd say is think about the function, and by that what I mean is think about the transformation. So if it's a scalar multiple, so 2f of x or k, or f of x is now equal to, right, if it's a scalar multiple, so f of x is now equal to k f of x, right? Well then remember, if it's a positive number, sorry, if the number is greater than 1, it's not a fraction, it's a whole number, then it's going to be a squeezing in of the function or stretching out of the function. So squeezing horizontally or stretching vertically. If it's a fraction, so if k is less than 1 but greater than 0, then what you're going to find is going to be a stretching out horizontally or squeezing down or shrinking vertically. So just to repeat that one more time, if k greater than 1 or a whole number, then you are squeezing the function in or pulling it out vertically. If k is between 0 and 1, so it's a fraction, then what you'll be doing is you'll be stretching it out horizontally or shrinking it vertically. Second transformation that we dealt with, I'll just keep it there, second transformation we dealt with is a f of x is equal to f of x plus k. So the adding or subtracting of a constant depending on the value of the constant. If the constant is positive, then it's just a positive shift up. If the constant is negative, then it's a negative shift down, and that's all depending on the value of the constant. And the third transformation we looked at was a reflection about the y-axis. So f of x equal, or that's the new f of x is now equal to negative f of x, and it's just a reflection about the x-axis, and all you need to do is take the original points and make sure that they are symmetrical. Once you've done all of this, you can check it by looking at the original points and making sure that if you compare similar x values, are they reflections about the x-axis? Is the x-axis a line of symmetry between the 2 points? Right? So that's the third one. And if we look at f of negative x equal to f of x, our last one, reflections about the y-axis. Once you've done all these steps, you can check by saying, well, as every point with similar y values, are they reflections of each other about the y-axis, right? Is the y-axis the line of symmetry between the points? So that's how you check it, guys, and continue to practice. Try drawing for yourselves. Sorry that the images are not so good, it's quite difficult on the whiteboard, but I'd encourage you guys to try it for yourselves, always use your ruler, and since these cubic function questions specifically are about graphs, you want to make your graph as accurately as possible, because this is different to when you draw a graph for yourself or when the graph is part of the question, just to help you get there. But when the graph is the question, then you need to try and make it as accurate as possible. Make sure you label x-intercepts, y-intercepts, stationary points, at least 2 other points, and classify the stationary points so you know what type of stationary point you have. So that's important. You classify and use that to help you draw the graph. But yeah, thanks guys.